So I have been talking about the Bloch sphere, which as I have defined it, it is a geometric for two-component complex vectors, which we are using as a description of a qubit. So I will tell you more things about it. The last time I described that the angles theta and phi for this spherical coordinates are chosen in such a way that orthogonal vectors corresponds to diametrically opposite points. Okay. And that is something you have to keep in mind. And now I can do many more things starting with that. So let me draw a sphere as well as I can. With the usual Cartesian coordinates, this 0 state is here, 1 state is here, and some generic point which I will call psi, described by the polar angles theta and phi. And how are these angles picturized? So you draw what is called a great circle or a longitude, which passes from north pole to south pole and goes through that particular point. And then the angle from this, wherever it intersects, I have to draw the equator. So let me say the equator will be something like this, and then it intersects the equator at this particular point. This angle is called the phi, which is the longitude, and this angle is called theta, which is the polar angle. Okay. And I wrote down this vector also explicitly, which was the overall phase not important, cos theta by 2 e raised to I phi sine. So now something which is needed quite a lot. Suppose I start with some fixed state. In computation, that is generally taken as the 0 state. Everything starts with 0. How do I reach this point? Okay. And obviously, the easiest thing to imagine is you travel around the great circle and reach that particular point. And these great circles are all, so in geometries, they are called geodesics, which means they give the shortest distance between the 2 points. And we have enough examples of this. For example, when airplanes go around on the surface of the earth, they don't necessarily follow the latitudes, which are the circles like this, because they are not the shortest path, but the geodesics are. So if you have a flight going from, say, Delhi to San Francisco, it doesn't go via Europe, it just goes over the North Pole. Okay, that's the shorter path, and that is where you save fuel. But this is an important property, that the shortest path on the spheres are all geodesics. And how are they defined? Which is basically 2 points on the surface and together with the origin. So if you take 2 points, this, together with the origin, draw a plane which will intersect the sphere in some place or the other, and the intersection arc is the geodesic. Okay, so for the 3 points, you can always draw planes, and this is the easiest way to visualize how the geodesic is going to look like. For any 2 points, it works. This is a particular case. So now I want to find this transformation. Okay, so the transformation to go from 0 to psi. Clearly, the geodesic is a rotation. Okay. And it will be a unitary matrix. What is that unitary matrix? That is what you want to determine. You are given this state. So you have this u 0 equal to psi. This is what you want to achieve. What is 0? 0 is the 2 component vector. The first number is 1 and the second number is 0. So I can easily write down U is equal to a 2 by 2 matrix. That is what it is going to be. The first number, whatever is over here, 0 state will be 1 here and 0 here, and that has to go into psi, which will look like this. So it's obvious that U will be made by 2 columns, and the first column of U is psi itself, because it takes 1, which is the first component, into psi. What is the second column? Well, it's a unitary matrix, and the second column will therefore be orthogonal to psi. We saw what that orthogonal vector was, the diametrically opposite point corresponding to this. Okay. So it is psi perpendicular, but up to some overall phase which we can't say in the orthogonality condition. How will I determine the phase? Well, you put in some arbitrary amount and make sure that the determinant of U is equal to 1. Okay, so this phase because we are using matrices with unit determinant. Okay. And I will write down this thing explicitly. So this is cos theta by 2 e raised to I phi theta by 2 what was the opposite components? Let me follow the convention which I used. It was okay, so I will put those things properly directly. This turns out to be this, and if you look at what the vector I wrote down last time, it is multiplied by minus e raised to minus e phi. Okay. So So I have to take down the psi perpendicular which I wrote down, multiply by this phase, and then it takes this particular form, and the determinant is 1 because you now multiply cos square theta by 2. When you multiply this cross term, the phases cancel out and it becomes plus sine square theta by 2, and that is equal to 1. So this is a general rotation which will take the 0 state to any arbitrary point on the sphere specified by this angle, and this is something which we will use. It is a 1 qubit rotation gate. It's a logic gate for the computation. One can see more things from it, because I also wrote down a very general expression for this unitary matrix for this 2 by 2 objects, which was exponential of minus I some unit vector which I simplified by evaluating the exponential series. To be this. Now you can ask what is the vector n which will produce this particular matrix. You can work backwards and expand this and figure it out, but geometrically it can also be seen that if I am performing a rotation, the rotation will be having an axis which is perpendicular to this geodesic circle, and the angle will be, in this notation, will be the theta, which is just the angle how much you rotated our geodesic, and you have to follow the what you call right hand rule convention about which is the axis and how do you rotate. It can be worked out, and because the geodesic is going through the two poles, this great circle will be perpendicular to a direction which is in the xy plane, in the equatorial plane. Okay, so it will be some vector, it points in this way. So yeah, let me just draw it, something like this. And if I rotate by right hand rule about this axis, I will go from here to here. And you can ask what is this vector in the equatorial plane, and the z component of it is obviously 0. It will have only sine x and y components, and you can work it out what this n is. And it is minus sine phi cos phi and 0. The x component goes negative because it's pointing in that way, y component remains positive depending on the value of phi. Okay, so this is another way of writing the same matrix. You can also write it at that. It does the same job. Now comes an interesting question, which is understanding the geometry of rotation. Okay. So this is u of theta and phi. And you can easily plug in the value and get a result u is equal to minus the identity. What does this mean? It clearly satisfies the determinant u is 1 because there are 2 minus 1 and it will multiply to 1. So we have not violated anything, but it is not identity. And mechanics, generally you learn that you rotate by 2 pi, you should come back where you are. It's not coming back where you are. So it is something different. And question is the mathematical artifact of what we have been inventing our notation, or there is something very much physical about it? So the answer is this is physical. It's not a mathematical artifact. And for that reason, these half angles which you have been sticking in just for choosing some convention are also very much part of the real world. So for 2 pi you rotate, you don't come back to your starting point. And there is a well-known demonstration for it. There is nothing to do with quantum theory. When I said physical, it is a property of the rotation group. Doesn't matter whether you are dealing with classical physics or quantum physics. So let me give you an illustration of it. If you have not seen it before, it is certainly worth remembering. You rotate a standard, some object by 2 pi. In classical physics, you come back to the starting point. But those are all the properties of what are called rigid bodies. The structure is not flexible. If you rotate by 2 pi, you come back to where you are. But if the body is not rigid, then the 2 pi rotation doesn't come back to the starting point. It does something else. And the well-known illustration, theorist's experiment, so to speak, is look at the rotation of my hand. I am rotating it by 2 pi. Hand has the same shape, but the arm got twisted. It's a flexible. And then I will rotate it by the same direction by another 2 pi. I came starting point, the arm is normal. So it's actually rotation by 4 pi which produces identity. This and this. And if you have seen some dances, classical dances, they do these things with a lamp in the hand, and they do it very fast. 4 pi rotation coming back to identity, but 2 pi rotation not. So this half angles which I have been sticking in all over the place, they have nothing to do with quantum physics. It's a property of rotation in the real world, whether it is classical or quantum is immaterial. And that is something which you should keep in mind, because it crops up in not only in this particular case, in many other examples, and sometimes there are all kind of descriptions involving topology and rotations which kind of seem unusual, like if you throw a cat down, it always lands on its feet. How does it do it? Well, you have to figure out. There is no angular momentum involved. it rotates with zero angular momentum. And that you have to figure out. And all these things kind of get involved in those topological arguments. Okay. So this is all I have to say about the geometry of a qubit, performing rotations with that, and understanding those things as a single qubit operations. Now I want to go to a different topic, and which is much more important in quantum theory than the vector space language which I have been talking about, and there is good reason for that, but it is not introduced that way in physics textbooks. And perhaps, yeah.
So like in this rotation you talk about kind of like a fermion or boson.
Yeah, so the half angle rotation actually corresponds to a fermions. So that is a property of a rotation group. It has many representations. The half integer representations will land up with these half angles, and they correspond to fermions. The integer representations land up with complete angles, and they correspond to bosons. But that is something which comes next. For that you have to go into a little bit into quantum field theory, where you define the properties of so-called Lorentz group to construct all the representations for fermions and bosons. But yes, it is related. In particular, this representations of the rotations groups are all fully classified. They are what you call matrices. Well, you can write them as matrices with some quantum number j, and j goes from 0, half, 1, 3 half, etc., etc. So these are the rotation group irreducible representations. They are labeled by various values, and they have dimensionality which is 2j plus 1. This is a standard algebra of a rotation group, going a little bit beyond what I need. But if you take the spin half of this, it corresponds to two component vectors, and that is what this is. And this is a half integer value. If you take 0 or 1 or 2, etc., the matrices will be of the appropriate dimension 2j plus 1, and the integer value of the angular momentum will describe a boson. The next topic which I want to discuss is something known as density matrix. Why it is important is it is a, I will give the answer first. It's a quantum generalization of the classical probability distribution. How so, I will illustrate by working through various steps. But this is what makes it a powerful structure, and it goes beyond whatever I have described in this two-component qubit notation, which is all done using a vector space. So this is not a vector, it is a matrix. So it has more components. So for things which connect to this description, I first discuss what are called pure states. Okay. And for that, the density matrix, typically denoted by the symbol rho, is the outer product of the state vector with itself. What does it mean that if I write psi is equal to some coefficient in some basis, then this is equal to just this full expanded version, and if I now interpret that as a matrix indices, I is a row, j is a column, then ci, cj star is a particular element. So I can write it as in a kind of abbreviated form. Rho ij is the component along ith row and jth column. So that is just a definition. Now, what do we construct these vectors as? So it was not just this, but there were constraints, which becomes very simple in this language. One was the normalization. The vector is contracted with itself is equal to 1. What does this become? Well, how do I contract this thing? And the convenient way to do it is take a trace. Trace is cyclic. You have to remember that is always the case, that trace of you can permute it cyclically, the trace doesn't change. Okay, so you take a trace, I can take it around and contract it on the other side, and that will give you 1, and that is what this symbol satisfies. And what does this mean is now in this language, what is a trace? It's the sum of the diagonal elements. And we know what this thing was. It's in the vector notation, it was just a Pythagoras constraint, quadratically adding up all the numbers is equal to 1. Now it becomes a linear constraint, and that actually helps quite a lot. Here it was a quadratic As far as rho is concerned, it's a linear relation. Trace is equal to 1.
Here, trace AB equal to trace BA. Here it is used. Trace is cyclic. Here it is used.
How it is cyclic?
No. It is cyclic. Okay, it is a fact, but here it is used.
To convert this into that, I am taking trace of this equation. It converts this one into this. Trace of a number is a number. There are no matrices if I take it around.
A and B are column matrix and row matrix.
Yeah,
Yes.
there is no restriction on the dimensions in here. As long as you can perform matrix product, it is fine. Or if you want to, yeah, that's good enough. But this is not the only thing which has happened in this definition. The overall phase disappears because of this structure. One of them will have e raised to I delta, the other one will have complex conjugate e raised to minus I delta, and it's gone. So the constraints which I was putting on this vector are satisfied in a rather simple manner. And there are no extra degrees of freedom left. I don't have to, so it automatically describes what I said earlier when giving a quantum definition, a unit ray, and which is what the definition of a quantum state is. What else just follows from this definition? Can very trivially see that rho square is equal to rho. If I multiply by itself, there will be psi in the middle, but that is 1. And that gives that the eigenvalues of rho are either 1 or 0. There is no other solution. On top of that, trace is nothing but the sum of all the eigenvalues. So one eigenvalue is 1, all other I forgot to say here, this is a Hermitian by construction. Hermitian conjugate, you'll get back the same thing because Hermitian conjugate of this is equal to that. So it has very simple properties because of this, and mathematically all operators of this particular type are spatial, and one of the things is kind of obvious. We defined a property of anything which satisfies this rule, that rho is what is called a projection operator. Square of it is itself. So this is a very useful description of a quantum state.
What exactly
Hmm?
What exactly you mean by unitary?
That I had defined earlier in the discussion of quantum state. It's a vector in the Hilbert space where the overall phase is deleted. And rho has exactly the required degrees of freedom. Everything else is taken out. So I had described how many components will be there for a n component quantum state. The number was 2n minus 2, and that is exactly true. So it has precisely those components. So this is a kind of generic stuff, and it works in arbitrary space and dimension, whatever it is. What about this two component stuff, which we use for a qubit? What is the description? Well, not too complicated, because the definition is already here, and I have written down what the vector is there. But let's see what happens. So for a qubit, multiply this by its complex conjugate transpose. So you will get this multiply its transpose, multiply all the elements one by one. The diagonal elements are this square and that square, and obviously this trace rho equal to 1 is trivially satisfied. The off diagonal one will involve this phase. So this is what is the result. Just multiplying this by its complex conjugate transpose, nothing more than that. But we can simplify by using a little bit of trigonometry. And I will remove an overall factor of half to convert this half angle into full angles. Okay. So what is 2 cos square theta by 2? It is equal to 1 plus cosine theta. What is 2 sine square theta by 2? It is 1 minus cosine theta. 2 cos theta by 2 sin theta by 2 is sin theta. And the other half is this. So the half angles are gone. But you can observe this thing even more closely in the basis which is known to us, which is the polymatrices. So this one is nothing but identity. Cos theta on the diagonal is a coefficient of sigma 3 or sigma z. And this off diagonal terms I can write e raised to I phi as a cosine phi and sin phi, and again write that combination in terms of sigma 1 and sigma 2, and the result is this combination where what is this vector? Well, the third component was just cosine theta. Sigma 1 component is the real part of this, which is sin theta cosine phi. And sigma y component is the imaginary part, which is sin theta sin phi. And you recognize this vector as Cartesian components of the three-dimensional sphere, which is why I wrote it in this notation. It's just polymatrices, Cartesian coordinates. So now we have a completely equivalent description of the Bloch sphere. Half angles are gone, and if you given a point theta phi, I can write the corresponding density matrix directly as this, using only Cartesian components. Okay, so it's simpler. And of course, it is very useful once you get to this language. You can ask, what will happen under all these transformations, rotations, etc. It's again simple because I constructed the general state by applying a unitary transformation, and I can ask what will happen to this, and it is more general than this, so it doesn't require a qubit. So in general, what you call psi going to u times psi implies rho will goes to u rho u dagger. I'm just multiplying u on two sides of this equation, and this is a unitary transformation. quite general. But it's bilinear in the sense that this matrix will appear 2 times. Once on this side as U, the other side is the inverse or U dagger. So yeah, these are the properties of the pure states. Now we can look at what happens to the other parts of the quantum axioms, just definition of the state, but there were other things, observables, there was a measurement prescription, there was a Schrodinger equation. All will come out of this in a different language. So what is a observable? Well, we defined the operator which is independent of rho, some Hermitian matrix, it's another Hermitian matrix. But the only relevant part is when you measure that operator, you will get some expectation value. And now one can write down what is that which is had defined as this expectation value which is nothing but trace of rho multiplied by O, again using the cyclic property of the trace. And this is the reason that it can be interpreted as a generalization of a classical distribution, probability distribution. For any operator O, there will be some weight, and if you combine those two things, then you will get the average expectation value. The peculiarity compared to classical physics is that there is trace will involve n number of possibilities after multiplying the two matrices, but in QM, rho, and O may not commute. If they commute, then there is a general theorem of linear algebra saying that you can go to a basis where both of them are simultaneously diagonal. That is an exercise for you to prove. It's very simple assignment. But if this thing becomes diagonal, then it is just the weight multiplied by that operator summed over all the possibilities. That is the classical construction of a probability distribution. But in quantum mechanics, the two matrices may not commute, and then you cannot make them simultaneously diagonal. And the off-diagonal components then will contribute to the expectation value. The off-diagonal elements are complex numbers in general. So rho will have contributions which will go outside this notion of probability. You can call them weights, but they are not real numbers between 0 and 1. So you can diagonalize one of them. So if you, that doesn't matter, off diagonal components of rho act as non-classical weights. And all the novelty of quantum mechanics is buried in here. That you may have multiple operators, but they may not commute. If they commute, everything collapses to classical physics. But if they don't, then there are new things which you have to take care of, or rather, you can find whether anything useful can be done with those new things or not. A related feature which connects to again the interpretation of the probabilities appears in the description of measurement. So what was the measurement prescription? You take a vector and there is a operator which you measure. The operator has some I have to write some notation. So let the eigenvalues be lambda and eigenvectors be ei. So what prescription says that when you measure it, you will get one of the eigenvalues and the state will change to the corresponding eigenvector. And the probability will be the overlap of the state with the corresponding eigenvector. Now let us write all those statements in the language of rho. Okay. So what is the component? Well, it's not EI, but that is fine. It's defined in a quadratic fashion, etc. But what we are doing is taking the original state psi and projecting along this result, and then the probability was the mod square of that. So this was the statement which goes under the name of Bond rule. What happens was the probability was given by this particular expression. You take the component along the direction of the eigenvector and take a absolute value square. This can be written in many different ways, but the easiest way to write it as again use the trace. That's what it is. How often that observation is made, this is a probability, the projection. But the state after the projection is the eigenvector. an eigenvector can be converted to the corresponding expression for rho. It is just another vector in the space, no problem. So you can combine everything together to say that I will get state reduction, which is this is the probability, and the final state is nothing but EI in the same notation. And there is a compact expression for this, which is Pi rho Pi. Write it down fully, whatever it is. Pi is nothing but a projection operator. I can write it as a so this expression is linear in rho. Okay. And these are the directions which are the characteristics of whatever operator you measured.
Here, flow can be presented as this Pi rho Pi.
This is the state of the system after you perform the measurement. Okay. EI is nothing but the eigenvector. So the measurement projection rule says that after measuring, you will get this particular state. But it also says that what is the probability of that particular measurement? The probability is given by this. So I am combining both these steps, that this expression has both the final state and its probability together.
Probability as a coefficient. Here probability as a coefficient we are getting.
Probability is this expression.
This whole trace of rho Ei. This whole thing is probability.
Yeah, you write it down by brute force, no?
This is probability.
And because this expression is linear, all measurement so one particular result produces this, another result will produce something else corresponding to a different index I, and because everything is linear, I can add all of them up in the sense of a statistical sum, which is what I generically do when dealing with a probability distribution. So this is what happens to rho. It changes to something else, and this has another name, which quantum state reduction. This is what happens when you perform a measurement. Okay. It's a different expression compared to this. These are unitary evolution. But there is certain similarity in the structure. In particular, all these so-called projection operators are Hermitian. So it looks like that, but only difference is there is a sum over multiple possibilities. In the unitary case, this is deterministic. There is only one particular transformation which occurs when you perform a measurement. There are branches, and you can describe the multiple branches as a statistical distribution, and the general result for that then can be described that the density matrix changes according to this particular rule. And that is again connected with this statement that transformation is a quantum generalization of a classical probability distribution. That is how you add different contributions in a quantum state measurement. And it's a important feature of all quantum theory. Things become peculiar compared to classical one when these two stuff don't commute. If it commute, then this will all collapse to just a sum over a bunch of numbers corresponding a state, and this is the direction. The weights are already the diagonal elements in that particular case. If rho happens to be diagonal, then you can multiply these matrices rather trivially. But in the basis of the eigenvectors of whatever you measured, rho may not be diagonal. Then you have to evaluate it. So this is an important feature, but again it kind of explains what you have to do to generalize definition of probability from a classical description to a quantum description. There are many more degrees of freedom involved because this is a matrix instead of just a set of diagonal elements. And in this old language, you can re-express this thing as well. Huh? Yeah, I have to erase and write it. It's okay. if you go to the basis in which the operator is diagonalized and evaluate these objects. What do you get? I wrote down here this general thing was a Ci times I, but if I take I to be the eigenvector itself of this object, which is this, the whole structure will just pick up the diagonal elements, which are nothing but the squares of this coefficient. And this is what our original definition of the bound rule is. What happens to rho? It's a sum, a statistical sum. This is the probability and this is the final state. Why is this peculiar? Because whatever is buried inside this Pi is little more than whatever is there in the classical structure, and that arises from the fact that rho and this operator may not commute. But in the classical case, you will just write down identical expression, some probability and some state. Yes.
For operator O, we choose the eigenvector orthonormal set of eigenvectors.
Yes, O is Hermitian, so it will have always an orthonormal set of eigenvectors.
Can it be identity matrix?
No, it doesn't have to be. It can be if you want, but it doesn't have to be. It's an arbitrary matrix.
So it will not form the complete basis if it is not identity Pi.
Any Hermitian operator, the set of its eigenvectors will form a complete basis, whether it is identity or not. It's an orthonormal set of eigenvectors which will describe all the components in the space, vector space, whatever it is.
It may or may not be Pi is equal to identity matrix.
Pi is not an identity matrix, but the set of Pi form a complete orthonormal basis. If it is identity, everything will become trivial. Okay. Because you are actually not measuring anything. It will commute with everything, trace rho is equal to 1 will just reduce all the expression. Okay. One last thing which is useful to know is write down the Schrodinger equation corresponding to what I wrote down here. And that is also interesting to observe, nothing complicated. Just starting from this was the equation. Time derivative will give the Hamiltonian. Now I will just evaluate this. Not too complicated, that was the definition of the density matrix, etc. And simple chain rule of differentiation. First term is just h times the matrix, and we have to find this. For that, I will take the adjoint of this equation, conjugate and transpose. What happens on the left hand side? This psi will get converted to the other vector, and I will change to minus I. On the right hand side, H is Hermitian. So you take an adjoint, it will remain itself, except that the order will be reversed. So it will appear as psi on the other side. So this is, there is a minus sign. The order reversed because in taking a transpose, A times B transpose is B transpose A transpose, things like that. And the minus sign came because of this thing changed. And we have a well-known result. It produces the commutator. And all the non-triviality is buried in quantum mechanics when these things don't commute. They commute, everything will go back to classical physics, but things don't commute. And this expression explicitly demonstrates that. How the states are going to evolve? Well, states will evolve only if the Hamiltonian is such that it does not commute with the density matrix. If it commutes, state will not evolve. State in the sense of the rho. And all the jugglery which we will work with will therefore focus on finding Hamiltonians which will change the states in some particular manner or the other. That is the description of an algorithm or a computation or whatever you want to call it. You have to design those things to change whatever the state is in some particular manner. So this is a so-called differential form of the equation. The integral form is over here. Both are equivalent. If you want to integrate this, you can write this thing as in that language again as rho will be whatever I was writing, H this is the solution of this equation in time order. It's still a linear equation, a differential equation. Rho is linear on both sides, and so you can integrate it. And only thing you have to worry about this commutator, how will it appear? Well, you can write it in this bilinear form, which is what I had implicitly done over here. And this was the same operator U which we are using in Schrodinger equation to describe the evolution. It appears twice. You can easily verify this by taking the time derivative. One time derivative will appear on this factor, which will give minus IH times the same thing. Another time derivative will be here, which will give plus IH, but on the other side, and that is exactly the commutator. This I is the consequence of taking this on the other side. It will become minus I. So all the machinery, whatever we have, can be converted into this particular language, and things work out fine. The most important feature is that everything remains linear in the density matrix. There are no quadratic expressions at all anywhere. So in the vector space language, you have to deal with things like this, square of the coefficient. You never have to deal with any squared objects. They are all linear, and you can do additions of those things very easily. You can express those as a probability combinations, etc., also in a straightforward manner, and things go through. But all these things give rise to an extension of the formalism, and which I will discuss in the next class. And that extension creates what are known as mixed states. See, whatever here I described so far was something which is called pure states. And the peculiarity of this mixed state is that it is not possible in the vector space language. There is no analog of it in the vector space description, but for the density matrix it is fine. And in practice, this is very much needed in dealing with lots of real design and what you call performance issues. You do not have pure states for a system which interacts with the environment. And such things are called open systems. And so density matrix is very useful in describing these open systems. These pure states are something which are labeled as closed. That there is no interaction of the system with anything outside, but open systems require inclusion of effects which come from outside. And the real world is like that. You cannot have a complete shielding, and as a matter of fact, measurement itself is an interaction of the system with the instrument, the apparatus. And we notice here that something additional is happening compared to just a unitary evolution. And so you want to deal with open systems, whether it's a measuring apparatus, whether it is an environment, whether any other description that you can come up with, it is absolutely essential that you understand the language of density matrix. And we'll give a what we call description of what happens or how to include these open systems in a density matrix language. It becomes a much more powerful construction going beyond whatever I have discussed in a vector space. That is for the next class. I will stop here.